Okay, let's go back to Theorem 8 and Theorem 9 and have a look at the proofs. Okay, so what am I doing here? Well, this is the inverse formula. Let's start with, we know that A times A inverse is the identity, right? So A times, what are we going to call these columns? Well, we got a bunch of columns here for A inverse, right? And we'll just pick one of them to think about. And we'll say this is the jth column of A inverse, and we will think about that. For the identity matrix, you can, well, the first column is E1, second column is E2, all the way up, and we'll say this is n by n. Okay, if you think about this multiplication, A times A inverse, what you get is you get A times X here, right? That was our definition. And you'll get EJ that it corresponds to on the right-hand side. So we conclude that AX has to equal EJ. Okay, so what do we do here? We apply Cramer's rule to this system of equations. Okay, so Cramer's rule says that xi is going to be determinant of A on the bottom. And then on top, you get A, I, and then we put, remember you put the B, you put the B there. So I did Cramer's rule. Now we're getting closer. We have this division by the determinant here, which is making us happy. It's important to maintain morale while doing proofs, you know. You have this determinant of A appearing downstairs, and you say, ooh, that's good. Ooh. The numerator, though, you have to contend with. What is that? Well, that is the part I'm going to fudge here. You need to think about, you know, what is being said here. What does this determinant look like? Well, I'm going to leave that to you. And for you to convince yourself, that's going to be CJI. So that's maybe the most tricky bit here, is just seeing that we actually have this determinant. So what was this going to say? the IJ minor. So you don't get CIJ appearing here. You get CJI, which is why we end up with the transpose in our final formula. Let me say, okay. So the IJ entry of A inverse, which is what we were finding right here, is this fraction. And so therefore, A inverse is actually the transpose of this matrix Cij. Okay, where Cij is this matrix filled with the cofactors. Okay, so a few gaps there that you'll have to fill in. The main one being this step. You have to, I can say it in words, but I think it's best if you just focus on what that determinant is and convince yourself that this is what you get. And that's the hardest part, I think. Let's look at theorem 9 as well. So what is this saying again? Theorem 9. We'll do the parallelogram. So it says this absolute value of a determinant is the area of the parallelogram determined by columns of A. Okay, let's go through this step by step. We'll say sketch of proof again. Gonna be a few gaps here again, which I'll leave to you. Let's go into parts here. Part 1, the absolute value of the determinant of A is equal to a simpler thingamabob. So the idea here is that you can take A rather, and reduce it to get D, where D is diagonal. No, so think about a 2 by 2 matrix A. So A is equal to A, B, C, D. It's possible to reduce that to this echelon form. And it's possible to do that using only replacements and interchanges. Okay, it's possible to do that. Okay, I don't have to do any scalings to get here. If I wanted to have ones in the diagonal, then I would need scalings, possibly. But I can get this far with only replacements and interchanges. That's important because replacements and interchanges do not change the absolute value of a determinant. Okay, so recap here. It's possible to take A and reduce it to D using only replacements and interchanges. And because I only used replacement and interchanges, I get this formula here. Okay, what is the determinant of D in absolute value? Well, that is the area of the rectangle, right? determined by E0, 0f. Okay, there's all kinds of problems if E or F are 0, but we're just going to fudge that for now. It's part of the reason I said sketch up here. Didn't want to get bogged down in details. And the last one is to say that the area, this area referred to here, is equal to the area of the columns determined area of the parallelogram determined by columns of A. Okay, so this part 3 is the hardest one to see, I think. Okay, your book has a nice diagram. Book has a diagram to convince you of this. Okay, if you're restricting yourself to replacements and interchanges, you're not changing area. Okay, so putting this all together, we say the area that we're looking for is equal to this area, which is equal to this, which is equal to the absolute value of the determinant of A.